So, welcome back. I'm going to talk about advanced inference in OWL, and I want to start this new video lecture of the Knowledge and Data course with a recap of what RDFS was, and by this I want to show that RDFS is in principle very useful for some applications, but in many others it's not rich enough, and that there are just problems with this in some domains where you want to have a more expressive language to model your domain, model your information and the knowledge that you have. So the reason for doing this is that we want to prevent miscommunication amongst web-based information sources, and we want to do this by this notion of predictable inference. So again, we want a language to describe the world and the domain with formal semantics, so that everybody who gets this data also gets the same results when they query it and when they want to do inference over it to get some implicit information out of the data. There is a good introduction in the Semantic Web Primer in Chapter 4. There's also an OWL primer available on the website, and we highly recommend you use the Protégé OWL tutorial, which will give you a step-by-step introduction to how to model an OWL ontology. All the links are, of course, available on the website. So let's think about what RDF was, Sparkle was, RDF schema, and a short recap. The main idea comes from this knowledge representation principles, that we want a formal language, so one that is machine interpretable, so that we get, whenever we have a query and whenever we have inference, that we get the same results, as long as we agree upon the formalism that is used. And we do this by giving a reserved set of symbols. So in propositional logic, this was implication or equality in mathematics, or union in set theory. And in the case of the semantics we're talking, we have this ISA hierarchy in semantic networks, but also in RDFS. And then basically you have a set of variables that you assign values to, and your logical notion of entailment is then based on assignments of values to those variables. So you have in propositional logic often the letters P and Q. In Sparkle, you have the variable names usually with a question mark starting X, question mark Y, and so forth. And then we have a set of entailment rules for manipulating the formulas, like the syllogism from Aristotle or modus ponens in propositional logic, like the ones that you implemented last week in the third assignment. And they allow us to derive consequences, entailed formulae that are true because not of the interpretation of the variables, but because of the structure of the argument. And that basically means that particular statements were true about types, relations between a type and a class, and then subclasses between classes. And because we have the knowledge about what these type of and subclass of mean, we can derive facts, not because we know which element is a type, but because we understand what type means. So there's a semantics assigned to the type, RDF type, and to the RDFS subclass of, and because of the semantics that is assigned to these reserved symbols, we can derive new facts. And this is predictable inference because everybody who applies the same entailment rules will get the same results. And so there's some correspondences with reality. So we try to make our semantics, our model theory, as realistic as possible. So we interpret classes as sets, and we interpret graphs, RDF triples as graph statements, and so forth. So that is the trick about logic, that you try to have your semantics as meaningful as possible. But once you've done that, you only do formal reasoning based on the notion of entailment. So basically, your knowledge is then expressed as a set of axioms or formulas about the world, and then later you can apply the rules to. And these formulae, they restrict the possible interpretations of the world, which we call the models in our logical language. So this is the theory side. Now we get to the more modeling side, and there has been in the past 20, 30 years an agreement that it really makes sense to distinguish generic knowledge, so schema knowledge, from factual knowledge or assertional knowledge. On the ontology level, if you model an ontology, then you talk about the classes and relations between classes. And if you talk about the instance level, then you have it really about the individuals that you want to talk about, the instances of your classes. You can also make the distinction between the schema level or the data itself. So what are the attributes of a table and so forth. In the ontology terminology that we're using here, you also make a distinction between the terminology, so the concepts that you talk about the world, and the assertional knowledge, so the facts that you really want to state. And in the jargon, you might see often that the terminological knowledge is called a T box, and an assertional knowledge is called an A box. So the generic knowledge is usually represented by means of classes, and that is usually meant to be a set of individual objects. And real objects then, so we talk about furniture, and then everything that is a chair would be a piece of furniture, but we can also have the classes of chairs, which is then meant to cover all the individual objects that have the properties of being a chair, which is usually 4 legs and something you can sit on and so forth. Cars and dogs, that's a kind of class descriptions of multiple objects. The factual knowledge is then represented by means of individuals. So I talk about a specific object, an individual that is in reality tangible. So this chair, that car, my duck, and so forth. And finally, there are obviously relations between those objects, and there are relations between those objects and the classes that they belong to. And those are modeled then as properties or roles or relations. And those properties are represented, if you do that in reality or in your model theory, then they are represented as pairs of individual objects. An RDFS schema is a language that allows for basic inferencing. So you can specify that something is a class. So in this case, this example country is of type class. And so you give each of them this something, a URI, and resource identifier. And you define it to be a class, which means that you are now referring to many objects that share some properties, namely that they are countries, whatever the properties are. This is a very generic statement that is not really necessary in many of your own ontology modeling applications. The next one is more interesting because it really gives some interpretation of the world that you want to give it. Namely, for example, that the Netherlands is of type European country. So you want to state that something is a member of a class. The next thing is that you now not talk about an instance in a class, but you talk about 2 classes and you want to relate them. So the European country is related by a subclass of relation with the country class. And that basically means that whenever you have something that is a European country, it must also be an element of the country class. Then you can say statements over properties. So the contains a city relation has a domain country, so it can only be applied to countries. And it only gets the argument, it only returns cities as an answer. So if you have Germany contains city, then the range of this contained city will restrict everything that is in this relation to cities. So you will only get cities back from when you query for it. And you can have some specific relations between properties. So a subproperty of has capital if you say has capital, a country has a capital, then this is a subproperty of contained city, because whenever something is a capital, it must also be a country, a city in this particular country. And from these facts that you state in this way, as we did here, you can derive new facts by inferencing, by simple inferencing. And this is the power already of RDF schema, which is quite some richness already. How did we do this reasoning? I mean, you will know because you have implemented some of those rules, I hope, and I expect you to have. Basically, you look in your knowledge base what kind of statements are in this knowledge base, and you can add new information because we know that it is logically entailed. So, for example, if we have, I think the next one are the more interesting ones, that if you have a fact that S is a subclass of Y and Y is a subclass of Z, then by the definition of what subclass means, we can derive that S is a subclass of Z. And the same for all the other axioms. So this is nice because it allows us to derive new facts, new inferred facts, new entailed facts, new valid facts according to the definition of my world that I gave in my knowledge base. The nice thing about these entailment rules in RDFS is that they are also complete. So that whenever you apply all the rules as long as you can, then you derive all the implied facts. So everything that is logically entailed, everything that holds with respect to your knowledge base will be derived if you apply those rules as long as you can. So that's very powerful, and that's one of the typical notions in logic, that you have in calculus, a rule system that calculates all the correct answers and only the correct answers. And the RDF schema rules, they do exactly this. So now, given the things that we can say about our domain with RDFS, this is a typical example of the things as we explained last week. You want to, on the ontology level, you want to talk about classes, so European countries and classes and properties, and how are properties related to each other. So we have the example has capital relation that is a subproperty of the contained city relation, as we said. The contained city relation has a range city and has a domain country, and European countries are subclasses of countries, and this defines basically the schema of your ontology, namely the relation of the classes of the sets that you are talking about. But we also have the data, namely that the Netherlands has a capital Amsterdam and that it is a European country, and that the Netherlands is a capital, and so forth, and a city. Some of this information we can derive by these dotted lines, by the inference rules that you have seen on the previous slide and that you have implemented yourself. And some of them are the stated ones, which are the fixed lines. And the nice thing is that in the last assignment, you have seen how to derive these dotted lines. And in the one before, you have already seen how easy it is to plot such a graph with the dotted lines as the inferred new statements. So this fits very well what you have done the last 2 weeks. So now what this allows you to do is that you can order your class, your instances. You can group them together in classes of instances and give general statements about them. You can relate things, individual things, such as the White House is in a certain city, or a certain city is in a certain country, and a group of people have one property, namely that they are male, so that's the class of man. You can have subclass relations, or you have relations between individuals again. This is all things that you can do in RDFS. But there is a lot of things that you cannot. For these things, the web ontology language has been developed, the language OWL. And this is basically, about having more power in your language so that you can say more things. So often you need more context rather than domain and ranges. So people live in houses while badgers live in sets. So the lives in relation needs to be defined in a more subtle way than just to say that that it only applies to people, and it only applies it only gives houses as an object. Properties may have cardinality. You want to say that the US has only one president and that a country has exactly one capital. You might want to give new characteristics to properties such as transitivity, so that if A is located in B and B is located in C, then you also want to derive that A is located in C. This is similar to the subclass of, but now you want to assign this transitivity property to a specific relation, namely located in. Or you want to say that something is symmetric. So if a country A borders a country B, then the country B borders also A. And you don't want to state this always twice. You can also say, okay, borders is symmetric. So whenever I see A borders B, then I also can derive implicitly that B borders A. So it's about class membership. We want to know whether an instance is an element of a class. And as I said before, domain and ranges are too blunt. They only apply when you really know everything about a property. And in many cases, you have very specific properties about classes so that you can restrict all the instances of it without doing this via domain and ranges. And we're going to see how this works. Another thing is that in RDFS, you cannot say the two things are the same. You don't have the means of saying my Amsterdam is the same as this Amsterdam. Something which you would have, for example, in the first task of the third assignment, really needed, would have been very useful to have. So one example, for example, is that you have the morning star, the evening star, and the Venus, and they are all the same object. How do you state that? You can't in RDFS. And then you might have complex relations with each other, and such as something cannot be both a city and a country. So this would be a disjointness. So the class of city and the classes of countries is disjoint. You might want to define something as the intersection. So for example, the presidents of the United States and the male people would be the male American presidents. You want the union of two things, you want the complement, and so forth. Some of these things are defined in Sparkle, but you want to define this on the ontology level, so already on your data and knowledge side. And finally, you also want to determine consistency, and you want to find errors of your knowledge base. And for this, RDF schema does really not give you enough. And for this, a new language is introduced, namely OWL, and we are going to discuss OWL in the next, all the different OWL operators and symbols, reserved symbols, in the next lecture. I want to make some general observations about OWL, because OWL has a rather long history now, and it is really an effort to reach a good trade-off between expressive power and computational efficiency. And this is one of the big stories of knowledge representation and logic over the past 30 years, I have to say now, because there is a restricted language thesis. General purpose knowledge representation systems should restrict their languages by omitting constructs which require non-polynomial or otherwise unacceptably long worst-case response times for correct classification of concepts. So this was what was said in 1991. Probably you don't understand a word. What this basically means is that we have knowledge enough about these representation languages and know how difficult it is to find inferences. There are some languages for which we can make statements, of which we know that it will take far too long, almost infinitely long, to get an answer. So you have a system, you ask, is this a valid inferred formula, and the system doesn't give you an answer because it takes too long to calculate it. So this is what's called the non-polynomial or unacceptably long worst-case response time. So you ask a question and your system doesn't say yes or no after some time, but it just waits, it just calculates. And there are two of these cases. The one is that it just takes too long, and the other one is that it's even impossible to give the right answers. So in the 90s and 2000s, people have tried to develop languages that were as expressive as possible without actually taking too long to calculate. So basically, description logics were languages that were devised in a way that they had as many operators and combinations of operators while still being very fast to calculate. And in the 90s, people came up with languages such as KL1, Loom, Classics, Chris, and then ALC and Chick and Shoin. These were the ones in the 2000s that really solved this problem. Basically, you still have a very high theoretical response time. So there's still language questions that you can ask to specific knowledge bases for which you will not get an efficient answer. But in most cases nowadays you can. So to summarize, the main challenge for devising these languages in which you can say a lot of things is that they can still be treated efficiently in a computer. And this is what the formal logicians such as Franz Baader or Doyle and Patil, what they were looking for, namely the richest languages that you can think of that are still easy to manipulate in a reasonably time. And OWL is one answer to this. It's a well understood, a very expressive language, highly complex, but it has still reasonably good computational properties, or at least these computational properties are well understood. That means that we all know that we can blow up every ontology reasoning tool if we do this cleverly, but in real life this won't happen. There are some things that you also need to know. There is no unique naming assumption. So if you have classes and instances with different names, they can be the same thing. So you need to explicitly say that two things are not the same, or you have to explicitly say that two things are the same if you want to reason with this. So the assumption is that they could be the same, but it's unknown. So there are now language operators in OWL that allow you to say these two instances are the same. Unless you specify this with this OWL same as, it is unknown. The same is that you can say they are not the same. This is closely related to the open world assumption, which says that nothing is assumed to be true or false unless it is explicitly specified or derivable from axioms or known facts. So if I have a knowledge base in which I say that everybody is a father who has at least one child, and there's a knowledge base in which I have no children, then this does not mean that you can derive that I'm a father. Because it could be that the information that you have about my children is incomplete, and you simply do not know that I have two children. So this is the open world assumption. As long as you do not know that something is the case or not the case, you cannot assume anything about it. This is relatively important when you define the semantics, so it's a formal thing, but it's also a practical thing, that you sometimes suppose that you could derive things which your tool doesn't give you back, and this is because you have supposed, you have assumed that a fact is false because it is not explicitly stated. And OWL will not, the OWL semantics doesn't work this way. What you can remember is that concepts are interpreted as sets. And the axioms basically restrict the potential members of this class. Again, it's the same idea we had before. You have your axioms state the restrictions on the models and the possible interpretations of your variables, and here it's the same. Your axioms specify which objects are allowed to be instances of your sets, of your concepts. This is on the theory side. So as we've seen before, you have an individual concept that is meant to be an instance of a more generic concept. This is sort of has its image in the world. The same is if you now use OWL and description logics, you have a statement which relates an OWL individual with an OWL class by some logical statement. And again, this is interpreted in the model theory now as a set construction. So you have your class is interpreted as a set of objects, and your instance is interpreted as an object in your domain. And there is this type relation if the object is interpreted to be an element of the interpretation of the class. And this is different from the semantics that we had before, because before on RDF we had an interpretation of a triple as a set, as a graph. So here we have a change in our model theory where we go away from an interpretation of a graph to an interpretation of a set and elements of a set. This has some consequences which we have to discuss later. A bit of terminology. We, as I mentioned, there is a distinction in knowledge representation between the instance level and the class level. And in description logics, this distinction was called the T box and the A box. So these are some terms that you might encounter in the literature and so forth. So the T box is the terminology and the schema, and the A box are the assertions. So it's the facts that you want to state about the objects in your domain. So summarize the web ontology language OWL contains features for defining classes and properties. It is built on a formal logic system called description logics. It is an extension of RDF schema, semantics and syntax, but only under certain limitations of RDFS, which are slightly outside this scope. But basically, it means that you really have to make a decision on classes and objects. Which of the things in the language you want to talk about are instances and which of them are objects. We tried to do this already in the third week, but strictly speaking in RDF schema, this is not necessary, and you can have both something to be an object and a class. If you try this in OWL, this will break. So there is really a strict separation of instances, classes, and properties. You need to define this, or you need to adhere to the usage. Let's put it like this. So if you once use something, A is an RDF type C, then A must be an instance all the time, and C must be a class all the time. There is some exception to this, but I will discuss that later.